Welcome to the central force problem. Today we are going to discuss the transformation of the scattering problem to laboratory coordinates. The scattering phenomena we have studied so far are two-body processes. We are interested in finding the laboratory angle theta, the angle between final and incident directions of motion in the laboratory coordinates. The scattering angle capital theta plays the same role, but for the relative vector in the center of mass coordinates. Theta and capital theta coincide only if the target particle is stationary. To obtain the relation between them, one must transform between laboratory and center of mass coordinates. And to see this, we will begin by listing the notations used. So the small letter symbols will be the final laboratory vectors for the position and velocity of the projectile particle of mass m1. The primed quantities will be the final vectors for the projectile particle in the center of mass frame, and the capital letters will be the vectors associated with the motion of the center of mass itself in the laboratory frame. So we know that the vector of a particle in the laboratory frame can be found from the vector sum of the position vector of the center of mass of the system in which the particle is contained and the relative motion of the particle to the center of mass. And from taking the derivative with respect to time for this relation, we find the corresponding relation between the free velocity vectors. Now, the target particle is considered to be initially stationary in the laboratory frame. So then momentum conservation reads as follows. The final momentum of the system, which is the momentum of a system having the velocity vector capital V and the sum equal with the and the mass equal with the sum of the masses of the two particles, has to be equal with the initial momentum, which is just the initial momentum of the projectile particle. So we can solve this relation for the center of mass velocity to obtain it in terms of the initial velocity of the projectile and the reduced mass of the system. Now, the normal and parallel components of the final velocity to the incident direction in both frames are related geometrically by the following two relations. So these are the normal and the parallel components of the final velocity in the laboratory frame of reference, written with respect to the components in the center of mass frame. So the parallel component has an added contribution from the velocity of the center of mass itself in the laboratory frame. And then from these two, we can immediately write down the tangent of the laboratory scattering angle as function of as a ratio involving the trigonometric functions of the center of mass frame scattering angle and the quantity rho, which is given by the expression here. So it involves the ratio of the reduced mass to the mass of the target and the ratio between the initial velocity of the projectile in the laboratory frame and the final velocity of the projectile in the center of mass frame. Now, furthermore, if we can square these two equations and add them up to obtain the formula here. And then if we take this together with the results 105 and 106, we can obtain another form of the relation between the two angles, this time for the cosine of the laboratory angle, as a ratio involving the cosine of the scattering angle and once again the quantity rho. Going all the way back to equation 3.2, we can write the final velocity of the projectile in the center of mass frame in terms of the relative velocity between the two particles after the collision in the center of mass frame, and the ratio of the reduced mass to the mass of the projectile. And this allows for an equivalent form of the parameter rho, as given here in as a ratio of the two masses, projectile to target, and the ratio of the initial velocity of the projectile in the laboratory frame to the relative velocity after collision in the center of mass frame. This last representation is important due to the following considerations. In the case of elastic collisions, then the initial velocity of the projectile is equal to the uh, relative velocity after collision in the center of mass frame. So with these being equal, then the parameter rho is given simply by the ratio of masses of projectile to target. In the case of inelastic collisions, a part of the kinetic energy is transferred into the internal excitation of the target, but momentum and total energy are still conserved. So in this case, the relative kinetic energy after collision is equal with the initial kinetic energy um, to, to which we add a negative quantity, which is the Q value or the internal excitation of the target. And then we can solve the system for the ratio of the two velocities relative to initial to obtain to find the square root here in terms of the Q value, the reduced mass, and the total energy, which is just defined as the initial kinetic energy of the projectile. And knowing this ratio, we can then once again calculate the parameter rho for this particular instance as having the expression here. Once again, assuming the hypothesis of elastic collisions, we can uh, derive in a simple way the formula for the recoil angle of the target particle. So we write down the parallel and normal components of the uh, target's target particle's final velocity in the laboratory frame as a function of the center of mass frame coordinates. So for the parallel component, we need to subtract from the relative velocity post collision. In the center of mass frame, we need to subtract the parallel component of the target's final velocity in the center of mass frame, and for the normal components, the simple equality holds. And then from this system, we can solve for the tangent of the recoil angle of the target to find the boxed expression here. Then we use these two simple relations. So the relation between the uh, final velocity of the target in the center of mass frame and the relative velocity post collision and the initial velocity of the projectile in the laboratory frame. So we have this relation, and then simply the conservation of linear momentum gives the second relation, from which we obtain the equality between v and v0, and we see that these two quantities are in fact equal. And then putting the two results together, we finally get the expression of the recoil angle in the laboratory frame of the target as a function of the scattering angle in the center of mass frame, and through very simple trigonometry, we end up with the basic result here. In regard to the differential cross section, it has to be noted that it also depends on which argument is used in the discussion. But the total number of particles scattered in a given solid angle must be the same regardless of choice of coordinates. So whether we express this in terms of the center of mass scattering angle or the or the laboratory scattering angle, the two quantities must be equal. So then we can find this relation between the differential cross-section written in the uh, laboratory scattering angle as a function of the differential cross-section written in the center of mass scattering angle and involving the derivative here. And using this result together with equation 3, 110, we immediately find the expression here in terms of the center of mass scattering angle and the parameter rho. So it is important to emphasize that both differential cross sections represent both of these quantities represent the same cross section, but it is written in different coordinates. One being the laboratory scattering angle, and the other being the center of mass scattering angle. In the case of elastic scattering, and under the assumption that the masses of the projectile and the target are equal, then rho is equal to 1, and from equation 3110 we find this simple formula between the laboratory and center of mass scattering angles. So the conclusion is the one given here, that the laboratory angle is half the center of mass scattering angle. So this conclusion is very important because it states that for elastic scattering of particles having equal masses, all scattering is in the forward direction. So this angle is always going to be smaller than this angle is going to be smaller than 90 degrees. Then if we go to result 3116, we immediately find the expression here, which is once again valid for uh, laboratory scattering angles smaller than 90 degrees and for the parameter rho being equal to 1. So what is important to observe is that even if the scattering is isotropic in the center of mass system, the differential cross-section written for the laboratory angle will still vary with the scattering angle. The only situation where the two are equal is the one in which uh, the target mass is much greater than the projectile mass, which will lead to rho tending to 0, and as such the two cross sections are approximately equal. As kinetic energy is transferred in all situations from the projectile to the target, collisions will always slow down the incident particle, and we can calculate the amount by which the projectile is slowed down through the use of the formulas listed here. So they lead uh, to the following ratio of the final to initial velocities for the incident particle. This is the expression here, and using this with the assumption for elastic scattering, so that rho is equal with the ratio of the masses, then we can calculate the ratio of the final two incident energies for the incident particle, which is the quantity here. And particularly if the masses become equal, so rho becomes 1, and then the ratio of energies is simply the squared cosine of the laboratory scattering angle. So in conclusion, when the center of mass scattering angle is pi, so when we have backscattering in the center of mass frame, then the laboratory scattering angle is at 90 degrees and the incident particle is stopped in the laboratory system. And this has a very important application, as it is the working principle of moderators in a thermal nuclear reactor. Fast neutrons emitted during fission lose velocity through successive elastic collisions until they are brought to thermal energies where they are more likely to cause further fission reactions than be captured. The ideal moderator in this case would be hydrogen, as it would result in the parameter rho being equal with 1, but in practice the moderators used are water, deuterium, or carbon-12. In laboratories, hydrogen is used to slow down neutrons as part of paraffin, water, or plastics. If we were to assume now that in the center of mass frame, the scattering is isotropic, so the differential cross-section is the same for has the same value for all scattering angles in the center of mass frame, then we can perform the following derivation. Uh, we know the relation between the cross sections as expressed in the laboratory and the center of mass frame. Uh, we know how scattering affects the kinetic energy of the incident particle, and we also know that energy is conserved, so the initial energy of the incident particle has to be equal with the sum of the final energies of the incident particle and the target. And we also assume that the impact parameter and and the final energy of the incident particle are in a one-to-one correspondence. So the scattering in from an element of the impact parameter S leads unambiguously to a scattering in a element of the final energy. So an equality of this form holds. Then we can solve this for the differential cross sections for scattering corresponding to a given final energy, and use the above relations to very simply find the result here. And we can do the same for the energy of the target particle, just based on the conservation of energy and the formula here to find the corresponding result. And obviously, to calculate the differential element, you just need to take the differential here and uh, work work it out. And so the sigma zero just follows from the. So it'll be a ratio involving this and the an element coming from the differential here, a sine of the capital theta and the differential of the scattering angle. Furthermore, in general, if we once again put together the connection between the laboratory and center of mass scattering angles and uh, the ratio between the final and initial energies of the incident particle the based on the angle of scattering, you can easily find well, we can easily show that this equality holds. So the scattering angle in the laboratory frame can be written in a way which involves only the masses of the particles, the initial and final energies of the incident particle, and possibly the Q value of the process is inelastic. The results of this analysis have been derived on the grounds of conservation laws for momentum and energy. For inelastic scattering, if the Q value is known, then structural details are irrelevant. The concern is only regarding ingoing and ongoing states, and it does not matter if the scattering process itself is classical or quantum in nature. Thus, quantum phenomena can be treated in this formalism as long as the scattering is non-relativistic. In summary, we have derived the transformation of scattering angles and cross-sections from the center of mass to the laboratory frame using the conservation of momentum and energy. We have briefly discussed special cases and applications such as working principles for nuclear reactors. In the following, we will discuss the free body problem. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.